In this video, we're going to talk about rational functions and models. We're going to start with sort of a review on how to solve rational equations and inequalities. So let's take a look at the first example. In the first example, we have what's called a rational equation. This is because you have basically a polynomial on the bottom and a polynomial on the top. So here, how do we solve rational equations? Well, the idea is you want to first clear the denominators. And so to clear denominators here, you can actually, if you multiply by 5, that'll clear out this 5. And if you multiply by x plus 3, this will clear out this x plus 3. And kind of for free, it's going to clear out this 5x plus 15. Because notice, if you multiply this together, you actually get 5x plus 15. And so 5x and 5 times 3 is to 15. So if you multiply everything by 5 times x plus 3, it's going to clear the denominator. So we're going to do this a little bit slowly here so you can kind of see how it works. So you're going to multiply this 4 divided by 5x plus 15. This will be multiplied by the 5 times x plus 3. So you multiply this by that, and then you also multiply this by that, so this will be equal to, and then you'll have the 4 divided by x plus 3, so 4x plus 3, all times the 5 times x plus 3. And then finally you'll have plus the 4/5, and it will also be multiplied by the 5 times x plus 3. And so what you want to notice here is what cancels. So over here, this entirely cancels, so that denominator is gone, and you just get a 4. Over here, just the x plus 3's will cancel, so you get a 4 times 5, which is 20. And then plus, over here, just the 5's will cancel, and so you're going to get a 4 times x plus 3. And then we'll distribute that 4 through, because we want to solve this for x. We'll take 4 times the x and 4 times the x plus 3, and we'll get 4 equal to 20 plus a 4x plus 4 times 3, which is 12. And so what do we have? We'll collect those like terms. So we have 20 or 32, because 20 plus 12 is 32, plus 4x. We'll move over that 32, so subtract 32 from both sides of the equation. And so what happens is on the left-hand side of the equation, we get a negative 28. And on the right-hand side of the equation, we get 4x. And so to solve for x, since we're multiplying by 4, we do the inverse, or the opposite in a sense, and divide both sides by 4. And so you get negative 7 equal to x. And that should be our answer. Now, you want to make sure you always check your answer when you're solving rational equations, but if you plug in negative 7 here and add 4/5 to it, you'll see you get a number, and you actually get exactly the same number if you plug negative 7 in over here. But you do want to check your answer to make sure it makes sense. The next thing we're going to look at is what we call solving rational inequalities. So here's our example we're going to do. And remember, when you solve an inequality, what we want to do basically is we want to find the zeros, and then we can plot the zeros on a number line. Now with a rational equation, we're also going to have, or rational inequality, we're also going to have, besides the zeros, we're also going to have what are called vertical asymptotes. So the vertical asymptotes happen when the denominator is equal to 0, and of course the zeros happen when the numerator is equal to 0. So the idea behind this one is you not only set the top equal to 0, but you're also going to set the bottom equal to 0. So 4x, so x squared minus 4x minus 5 is equal to 0. So these will give us the zeros of the function. And then the bottom one, x squared minus 9x plus 14, typically gives us the vertical asymptotes of the function. So this one is x minus 5 times x plus 1 is equal to 0. And so we're going to get two answers here for zeros, x equal to 5 or x equal to negative 1. And then this one, so remember how we factor, it's x plus or minus something times x plus or minus something. The something depends on the 15, and so 15 is what? It's 3 and 5. Oh, I just noticed I copied that down wrong. So that's not supposed to be 15. That's supposed to be 14. So let's change that to 14. Alright, so that's better, because I was thinking 3 and 5, no way to get 9. But 14 is 2 and 7, and you certainly can get a 9 from a 2 and a 7. And it's negative 9, so it's minus 2, minus 7. And so that makes x equal to 2, or x equal to 7. So what we can do now is we can put these on our number line to draw our sign diagram over here. And so let's put those numbers on there. And so what you have is negative 1, and that's a 0. And then you have 2, and 2 is actually a vertical asymptote. So if you want, I'm going to put a dashed line right here just so you can see it's not really a 0, it's actually a vertical asymptote. So it's basically what the function kind of blows up or blows down. And then we have 5 here. So here's 5. And it's a 0, so I'm not going to put a dashed line, of course. And then the final one is 7, and now that's a vertical asymptote, so I'm going to put a dashed line at 7. Okay. So remember, the idea of making this sign diagram is we find out where it's 0 or these vertical asymptotes, because that's possibly where you're going to switch signs, basically. And it's the only places you can switch signs. Remember, there's just 3 possibilities. This expression right here can be negative, 0, or positive. And so what we found is where it's going to switch sign, where it's equal to 0, so it's going to be positive or negative to the left or right, or there's a vertical asymptote, so that's where another place where you can kind of flip signs, and that's it. It's continuous basically everywhere else is the idea. Okay, so we need some test points. So let me find some test points here to figure out if it's positive or negative to the left or right. So probably here I'd pick, what, negative 2 would be the easiest test point. Here maybe I'd pick 0. Of course here would be 3. Here it'd be 6. Just a point in between the points like 5 and 7. And over here probably 8. And what you want to plug it into is this original expression. Now this original expression you can rewrite as it factored. So the top, remember, was x minus 5 times x plus 1, and divided by, and the bottom was x minus 2 times x minus 7. So it's easier to plug it into here because it's already factored for you. So you can see when you plug in negative 2 here, what's going to happen is you're going to get negative 7 on top times a negative 1, because negative 2 plus 1 is negative 1. And then you plug negative 2 into the bottom, and that's going to give you negative 4, and then times a negative 9. Now I don't really care about the numerical value. What I really care about is the sign. And you see a negative is positive, and positive by a positive is a positive. So let's put a plus there, and we'll do it in green because plus is like good stuff. And then let's plug in 0 now. So if we plug in 0, what happens? So I'll plug 0 in here, and you'll get negative 5 times 1. We plug 0 in the top, and now plug 0 in the bottom, you get negative 2 times negative 7. And so on top you have a negative number, on bottom basically you have a positive number. Negative by a positive is negative. Let's plug in 3 now to this expression, and we get what? Negative 2 times, if you plug in 3, 4. And then if we plug 3 in here, we get 1, and here you get negative 4. So 1 times negative 4. So on top you have a negative, on bottom you have a negative, so a negative by a negative is actually a positive. So let's make that plus. And then we'll plug in 6. And so when you plug in 6 here, you get 1 times 7. So 1 times 7. And on the bottom, you're going to get a 4 times a negative 1. So positive on top, negative on the bottom. Positive divided by negative is a negative. And finally, when you plug in 8 over here, you're going to get 3 times 9 divided by 6 times 1. And of course, that's a positive. All right, so now what do we want? We want when this is greater than 0. So we need to read it. And so over here, when you read it, this is not a less than sign, so it must be a greater than sign because it doesn't look at the letter L. So when it's greater than 0, it's when it's positive. So it's all this stuff here. And we don't want to include the endpoints because it's greater than 0. Then all this stuff between 2 and 5. And all this stuff to the left of 7. So when we go to write this down, what's it going to look like? So it'll look like this. It'll look like negative infinity to negative 1, union 2 to 5, and then union 7 to infinity. All right. Now things get a little bit more complicated when we think of, so this is my answer first. So first of all, this is my answer for this problem. Now I want to change the problem just a little bit so you can see how it gets a little bit more complicated when you bring in equality. So if you want greater than or equal to 0, then you have to remember some stuff. You have to remember that these numbers right here are the zeros, whereas these numbers down here are where the vertical asymptotes are occurring. So I drew those in my sign diagram to remind myself. But if I want greater than or equal to 0, what I'm going to need to do is I need to do negative infinity to 1. And then because that's where they have a 0, I would include 1. And then union, don't include 2, but I would have to include 5. And then union, then you would have 7 to infinity. So that's if you had greater than or equal to 0, you would have to include those 0 values there in your answer. All right, let's move on. Let's talk a little bit about what rational functions are. So rational functions, the idea is you have a polynomial divided by a polynomial. Typically, the graphs will look something like this. You have the function, basically, the idea is it blows up here, and then on this side it's blowing down. So you get what they're called these vertical asymptotes. You also get what are called horizontal asymptotes. They typically look, so like this one might look something like on the bottom, you might have x squared minus 4. The reason for that is because you have vertical asymptotes here at negative 2 and positive 2. And on top, it might look something like 8x squared. And the reason for that is you have a horizontal asymptote at 8. So as x gets really, really, really big, what happens is that the function approaches the height of 8. So you have x squared and x squared basically kind of cancel each other out at the end, and you can just get back to 8. But this is an example of a rational function. And you can think of them as thinking about them as sort of they have these sort of vertical asymptotes because you're dividing by something down here, which basically makes a function blow up or blow down at certain points. And sometimes they have horizontal asymptotes, so they don't just go off to plus or minus infinity all the time. Sometimes they'll actually approach a number in the end, to the right or to the left. So let's talk some more about these. All right, so we talked a little about what rational functions are. We talked about their formulas. All right, so the formula is a polynomial divided by a polynomial, where p of x and q of x are polynomials. Notice the denominator can't be 0, so we have to sort of say q of x is not equal to 0. And they have these horizontal and vertical asymptotes. So what we want to do is, from a graph like we saw before, it's pretty easy to identify vertical and horizontal asymptotes from a graph. So like, for example, here, this has a vertical asymptote at x equal negative 2 and a vertical asymptote at x equal 2. Whereas this has a horizontal asymptote at y equal 8. So from a graph, it's not really a big deal to find horizontal or vertical asymptotes. Remember, the idea of an asymptote, though, is the graph approaches the line at x equal negative 2, or a horizontal asymptote, the graph's approaching the line y equals 8 as x gets bigger. From a formula, it can be a little bit more difficult. So that's kind of what we want to focus on here. So what I have for us to do is I have 4 different examples. So I have this first example, 2x over x squared minus 36. And this next example, 2x squared minus 32 divided by x squared plus x minus 20. This third example, x squared over x minus 1. And then finally we have this fourth example, 10x over x squared plus 1. Each example shows us something a little different that can happen each time. So there's a sort of a purpose behind each of these. Let's do the first one, and let's just kind of go in order. First, let's just try to find the vertical asymptotes of each one. So for the vertical asymptotes, so remember the idea of a vertical asymptote. The idea is that the function either blows up or blows down. Basically, it's going to go to plus or minus infinity. And the way that these rational functions can go to plus or minus infinity is what? Well, the idea is that this denominator turns out to be 0, basically. So what we care about to find vertical asymptotes is we take the denominator and set it equal to 0, because that's when it's going to blow up or blow down. If you take a number up here, some number here, who knows what it is, let's say it's 12, and then you plug in 6 and you get 12, and then you put 6 down here and you get 0. 12 divided by 0 is like plus or minus infinity. So it's going to be a really big number. It's really undefined, but it's blowing up there. And so what we can do is we can set this equal to 0, and we can solve this for x, and that'll tell us where the vertical asymptotes actually are. So you can rewrite this as x minus 6 times x plus 6. We can factor equal to 0, and so we get two answers. X is equal to 6, or x is equal to negative 6. And so these are what we call the two vertical asymptotes for this function. And what we can do then is you can actually draw sort of a dashed line here at negative 6, because eventually we're going to graph this thing, so we'll put the information over here. And so we have a vertical asymptote at negative 6 and a vertical asymptote at positive 6. All right. Let's move on to the next example. So if we go down a little bit on this one, so now this one's a bit tricky. It's a bit tricky because you can factor the top and the bottom, and if you don't do this, you might make a mistake. So let's factor the top and the bottom, just so we can see what's kind of going on. So you can pull a 2 out of the top here, and you get x squared minus 16. And then the bottom you can factor as x plus or minus something, x plus or minus something, and if something depends upon the 20. So when I see 20, I think 4 and 5. Can I add or subtract 4 and 5 and get 1? Oh yeah, I can. So this I think is going to be minus 4, let's say, and this is going to be x plus 5. That should do it. And I can continue to factor because I can factor the top a little bit more, because the difference of two squares, x squared minus 16, can be factored as x minus 4 times x plus 4. And so what you want to notice is there's something kind of funny about this function. On the top you have x minus 4, and on the bottom you have x minus 4. What that actually means is that you have a hole in the function, not a vertical asymptote. So when you go to find vertical asymptotes here, so VA, find vertical asymptotes, you can set the denominator equal to 0. There's no problem with that. Alright, so set it equal to 0, because that's where the function you say blows up or blows down. And you can factor it like we just did, x minus 4 times x plus 5 is equal to 0. And so then you can say, either x minus 4 is equal to 0, or x plus 5 is equal to 0. And you get your two answers, right? X equals 4, or x equals negative 5. But just one of these is correct. So this is not, so let's put an x through it. This is not a vertical asymptote. It's actually a hole. And it's not too hard to remember because you do have a graphing calculator. So if you're stuck in a bind, you can always have this sort of this graphing calculator kind of going here, so you can see what's actually going on. So here's hit on. Let's hit y equals. Let's try to graph this thing. So when you plug this in, you have to remember you have to put parentheses on top, because this 2x squared minus 32 is all on top. So you have 2x squared and then minus a 32 in parentheses divided by left parenthesis x squared plus x and then minus 20. Right, so if you're going to put this in your calculator, that's how I do it. And then I really don't know where to look. So when I make my window, this window's set up for a different problem. I would just go to Zoom and go to Zoom Standard. It's number 6. It's just a negative 10 by 10 window, just so you can see what's happening. So you can see over here at negative 5, that's where that vertical asymptote is. But over here, something funny's happening. Right? What's happening over here is that there's no vertical asymptote at 4. And the reason there's not a vertical asymptote at 4 here is there's actually a hole. But it's really hard to see. You can't really see it. So on my graph, I think what I'll do is I'll draw a vertical asymptote at -5. So here's a vertical asymptote at -5. And you can see that on the graph on my graphing calculator. So here's my vertical asymptote at -5. You can label it if you want, x equal to -5. And I'm going to put a great big hole at 4. Now I need to know what the value of this thing is at 4, which is kind of hard to figure out. But if you look here, if you think about canceling these off, so because they kind of do cancel in a sense, you can plug in 4 here, and this is going to be 8. So 4 plus 4 is 8 times 2 is 16. And so you have 16 on top, and if you plug 4 in the bottom, you get a 9. So it's basically 16 over 9, which is a little less than 2. So at 4, you're going to have this sort of hole right here. All right, so that's the point 4, comma, 16 over 9. And it's a hole. It's going to be a hole in my graph, basically. And remember, the way I found that 16 over 9 is I just plugged 4 into here, just disregarding these x minus 4s. So I had 4 plus 4, which is 8, times 2 is 16, and then a 9 on the bottom. All right, so that accurately represents sort of that information there. Let's move on to the next one, which is right below here. We have an x squared divided by x minus 1. Now this one's going to work out real nice. So for the vertical asymptotes, we just care about when this thing's going to blow up. So that's when this denominator is equal to 0. So x minus 1 is equal to 0. And so you just solve for x. So you add 1 to both sides, and you get x equal 1. So right here, at x equal 1, we have a vertical asymptote just going down. So at x equal 1. And then down here, for the part D, this one's kind of interesting because when you look for the vertical asymptotes, of course you take that denominator and you set it equal to 0. So x squared plus 1 is equal to 0. And you try to solve this for x, so you can't really factor it. So maybe you think I can move it over, so you subtract 1 from both sides, take the square root, plus or minus the square root of -1. Oh, that's an imaginary number. And remember, we don't want to work with imaginary numbers. We don't want to work with complex numbers. So in this one, there's actually no real solution. We say no real solution because there is an imaginary solution. And so what that means is that for vertical asymptotes, there are none. So no vertical asymptotes for this one. Let's talk about horizontal asymptotes now. Let's go up to the very first one. So for horizontal asymptotes, these aren't too hard to find. There are a couple of ways to do it. I'm going to do it using limits. You don't have to use limits. You can just actually write down the answer if you want. But I always tell you I'll give you an extra point on the exam if you actually use limits. So for horizontal asymptote, remember the idea. The idea is if you look all the way to the right or all the way to the left, if the height of the function is approaching a value, then that's a horizontal asymptote. So the idea is just look what happens when x gets really big. Watch what happens when x goes to infinity of 2x over x squared minus 36. And so just think about what's going to happen. So up here you just get like 2 times infinity. But down here you get infinity squared. So it's kind of like you have 1,000 up here and you're taking it times 2 versus you have 1,000 squared on the bottom. So basically the bottom's going to get really big. The top's going to be kind of big, but nowhere clear near the bottom. So this is actually going to go to 0. And so what we want to mark here then is that we have a horizontal asymptote at y equal to 0. And we don't have to look to the left because with rational functions they do the same thing on the right and left. But what we'll do is we'll just mark let's do a little sort of dotted line in green here. So let's mark this little line right here, out here and out here, y equals 0. And I guess we should have down here, we should have written like x equals 6 and also x equal -6. All right. So with that information, we're about ready to be able to graph this thing. I think you can look, if you want, start with your graphing calculator. and we can just plug in the formula. So if you have it, let's hit y equals and come back here, and let's plug this thing in. So you have 2x divided by, remember in the bottom you have to have parentheses because you have an expression with a minus sign in it. So divided by x squared minus 36. Let's just go to, we're going to do a standard window, negative 10 to 10, so it's already set up for us. And we hit graphs, and you just get a feel for what it looks like. Right, so this is just sort of the form, the shape. You don't want to copy this down explicitly because this looks like a vertical line right here, but it's not. Okay, if you draw a vertical line on here, it's no longer a function. So what you want to do is just approximate. You see how it goes through the origin. That's because if you plug in 0, you're going to get out 0. So what we want to do is we simply want to approximate this graph. So when you look at it, it's like, oh, it starts here kind of and goes down. So over here, we'll do the same thing. We'll start over here, and then we'll just sort of go down. But we'll just approximate. We're just going to approximate it when it goes down. So down like this. And we'll delete that little here right there. So we're just approximating. It's not perfect, right? But it's good enough. We didn't draw a vertical line though, because that would be a mistake. Then over here, it kind of goes down and it goes across the origin right here. So, we'll start up here, kind of go down a little bit, right there, kind of shade it in to make it nice. It's hard to draw on here, but it comes down right here, goes across here, and then comes back. It goes down here, like that. And I'll shade this in because it should be concave down right here. That's good enough. Okay, but it does go through the origin. But notice it didn't go vertical on you, even though it looks like the calculator. Remember, the calculator is a tool of approximation, so it's just telling you approximately what it looks like. It doesn't understand that it doesn't really go vertical. That's not supposed to be a vertical line. And then over here, it does basically the same thing. It's going to start up here, and it's going to head kind of down here, and then head out. It doesn't head towards height 0. Right, and kind of shade it in a little bit. It's supposed to be concave up. All right, that's my best, right, with this drawing on this tablet. But that's what it looks like, basically. Let's go down to the next one, and let's find its horizontal asymptote. All right, so if a horizontal asymptote on this one. All right, so here, again, I'm going to look at the limit as x goes to infinity, which you can do if you want to. You don't have to do it. I'm going to show you a way to kind of avoid limits if you want to in a minute. We can just kind of think about what's happening with these expressions. So over x squared plus x minus 20. So think about what this is actually saying. It's saying as x gets bigger and bigger, what does this function do? So what it does, if you plug in a really big number, is you're going to square it and take it times 2 and take away 32. So taking away 32 from a really big number really doesn't matter. Like if you have a million and you take away 32, who cares about the take away 32? It's a million, right? So really all I care about is this x squared term times 2. On the bottom, the same thing holds here. You really don't care about these terms over here. You just care about this x squared term. So what's going to happen is that this is just going to go to, on top, it's going to act like 2x squared, so it'll be like a 2. And the bottom is act like an x squared, so it's like a 1. So it's going to head towards 2 as you go to the right. And the same thing's going to happen as you go to the left because it's a rational function. So my answer would just be y equals 2 for a horizontal asymptote. And so up here, what I want to do is I want to draw a horizontal line here. If you want, you can draw it all the way across if you like. It doesn't really matter as long as you draw it at the ends. So you have this horizontal line here at y equal 2. Okay. And we can look at this on our calculator. We've already done this, but let's look at it again. And then we might be able to graph it just based off that information. So left parenthesis 2x squared minus 32. In parenthesis divided by left parenthesis x squared plus x minus 20. So let's see what it looks like. And maybe from the graph then, since we know what the vertical asymptotes are and everything, we can kind of figure out what it looks like. Okay, so I kind of see it. All right, so the idea on this thing is what? The idea is it's going to start over here and then go up. So when I go on this, I'm going to start right here. I'm just going to kind of go over and then go up the best I can. And then I look at the graph again, and it's going to start down here. It's going to pass through the x-axis. It's going to actually pass through the x-axis at -4. You can see if you plug in -4 here, you're going to get a 0. So it's going to pass through here at -4, and then it's going to turn off here and just sort of head towards y equal 2. So this is not easy to draw on here, but I'll do my best. So it's going to pass through this -4 right here. So I'm going to put a point right here at -4. It's going to pass through this. It's going to turn off here, and it's just going to start heading towards, and there's a hole there. It's going to start heading towards, and then just put an arrow right there. It doesn't pass 2, it just starts heading towards 2. And then over here, it's going to turn downwards, just turns downwards here, and heads towards -infinity. So as soon as I get close to that, I'm just going to put an arrow on it. So it's clear that it just sort of heads down. And so that's my interpretation, right, of this graph, what it does. Now notice the graph didn't go back on itself. You have to make sure that it doesn't go back on itself. Right, it wasn't a horizontal line. It's actually not a straight horizontal line there. It kind of looks like it, but it's not. It's getting ever and ever closer to y equals 2 here. It's approaching height 2. And this continues to go ahead towards -infinity, getting closer and closer to the line x equal -5. Alright, so let's take a look at the third example and look at the horizontal asymptotes for it. So HA's horizontal asymptotes. And so here, again, you can look at the limit as x goes to infinity. Doesn't matter which way you go, plus infinity or minus infinity on these types of problems, because rational functions do the same thing on either side as you go farther and farther out. And so if x squared over x minus 1. And so on this one, what's going to happen, if you think about it, you're going to plug a really big number in, you're going to square it on top, and on bottom you have a really big number, you're going to take away 1. So what's going to happen, it's just going to act like that really big number. That x squared on top is going to dominate. So it's going to be huge on top, and it's going to be big on bottom, but just not as big on top. So it's going to go to infinity. So what that means is you're going to end up here on either side, basically, plus or minus. Oh, you have to be careful. I made a little mistake there. So actually, when you go to -infinity, it's, if you look here, so if you go to -infinity, it actually won't end on top. So think about this. If you plug in a really big negative number, it'll be big positive on top, but on bottom it's going to be negative, and a positive divided by negative is negative. So actually, as you go to the left, it's going to wind up down here. But it still means that there are no horizontal asymptotes, so none. But when we graph this thing, let's take a look at the graph. You're going to notice that it's going to end on the top up here on the right, and it's going to end on the bottom on the left. So y equals, let's graph it. And so let's clear this out. So left parenthesis, I don't need a parenthesis actually, so x squared divided by, and then you need a parenthesis, left parenthesis, x minus 1 in parenthesis. And then we're going to make our window, and our window is from -10 to 10 again. I think that's a fine one. Let's just hit graph and see what it looks like, because I really don't know much about the function. And so that's what it looks like. And so we can actually just graph it. The idea, it starts up here, then turns around and kind of goes up. So let's give it our best shot. So right here, kind of starts up here, kind of comes down. Ah, that's terrible. Let's go, just try this again. So it starts up here, and then kind of comes down, and then turns around and goes up. That's good enough, I think. And then over here, it basically does the same thing. It starts down here, kind of comes up here, turns around, kind of goes down like that. If I can make this any better, that's better. All right, so there's the graph of that function there. I think it looks good enough. Okay, so it does something like that. Actually, I should make this a little bit better. So notice it touches the origin. This one doesn't touch the origin. So we want to get a decent representation, and to get a decent representation, I should probably capture at least the intercepts here. So there's an intercept here at the origin. So I should at least capture that, right? So let's do it. Let's do this again. Should follow my own rules here. So make it look, doesn't have to be exactly like it, but as close as you can. Oh, that's terrible. All right, so kind of comes up, turns around here, and then starts heading down right there. Again. Try it again. All right. And then I get close, and then just make it go down. You don't want it to go back on itself. That's the deal. All right, and that's good enough, I think. I'll take it. I might shade this in just a little bit because it's kind of like a straight line. So this one's kind of funny if you think about it. All right, so when you look at the graph on your calculator, you kind of notice this has a sort of funny sort of line right here. This is what's called actually oblique asymptote. We're not going to talk about them too much. I'm not going to stress them, but there's actually right here what's called an oblique asymptote. So there's a line right here that it actually approaches. And again, I don't talk about it much, but you may see it in the homework. They may say something about it, right? But they call this an oblique asymptote. And we're not going to focus on them at all. We're just going to do horizontal and vertical asymptotes, but that's called an oblique asymptote. Let's do the last one. We're almost done here. So on the last one, we want to find these horizontal asymptotes. And so again, to do that, if you want the extra point on the test, you write down the limit as x goes to infinity of this function 10x divided by x squared plus 1. We can then interpret. So the idea is you have an x on top and x squared on the bottom. So basically the bottom's going to dominate because it's going to be so big. So it's like 10 times a million divided by a million squared. A million's a big number, and 10 times it's even bigger. But a million squared is so much bigger, it's basically going to force it to 0. So this has a horizontal asymptote at y equal 0. So there were no vertical asymptotes, but there will be horizontal asymptote here at y equal 0. And when you graph this one's kind of funny because there are no vertical asymptotes. So it doesn't blow up or blow down, but you can see what the graph looks like. So what we have on top is 10x. And then on bottom, divided by left parenthesis x squared, and then you have plus 1 in parenthesis. Delete all this stuff over here. Make sure that's in parentheses. Okay, so there's my function. Just hit graph. Let's see what it looks like. So this one kind of comes down, then goes right back up to the origin, then comes down again. So let's give our best shot at trying to graph this on here. And so you're kind of going to start over here. Start right here. It's going to kind of come down, go back up, turn around, and come down again. Good enough. It should be symmetric. It's not very symmetrical. I'm going to take it though. It's basically the best I can do on this tablet. But that's the idea. It captures most of the information. You know, comes up, comes down, comes back up. It looks pretty good. But notice there are no vertical asymptotes, basically. Okay, what? So I do want to kind of compare and contrast these just a little bit. So to do this, let's just kind of change. Let's zoom out just a little bit here. So let's see what this looks like. This is good enough. You can't read it, you can't see it exactly, but for my purposes, what I want you guys to see is when you do the horizontal asymptotes, they're basically just 3 cases. So what are the 3 cases? So case 1 is that the degree on bottom is bigger than the degree on top. So you'll notice here you have degree 2, and there you have degree 1. If that's the case, the horizontal asymptote will always be 0 because the bottom will dominate. So you really don't need to use limits if you don't want to. You can just say, oh, look, the degree is bigger on bottom, so it's going to head towards 0. This also happens down in this last case down here. You'll notice the degree on the bottom, which is 2, is bigger than the degree on top, which is 1. So we'll have a horizontal asymptote at y equals 0. So there's one case. The second case would be the degree on top is bigger. So if you look here at C, you'll see the degree on top is bigger than the degree on bottom. So you have an x squared on top and you have an x on bottom. This will mean there will be none. Basically what will happen is a function will blow up or blow down to plus or minus infinity, just depending on the expression. But there will be no horizontal asymptote. And then the third case is when the degrees are exactly the same. So that's part B. So here you have degree 2 on top, degree 2 on the bottom. And when that happens, it's just the coefficient on the leading coefficient on top divided by the leading coefficient on the bottom. So that's why it was 2 over 1, which gave us y equal 2. Right, so you don't really need limits in the case of rational functions because there's only 3 possibilities. Degree on top is bigger, which means there'll be none because it'll blow up to plus or minus infinity in the end. Degree on bottom is bigger, which means there's a horizontal asymptote at y equals 0 because the bottom will dominate, basically forcing it to 0. Or the degrees are exactly the same, and in that case you just look at the coefficients. So here the coefficient on x squared is 2, the coefficient is 1, so it's 2 over 1, so it's a horizontal asymptote at 2. So hopefully that made some sense. Alright, so to review, right? So we solved rational equations and inequalities. We talked a little bit about what rational functions are, a polynomial divided by a polynomial, and we talked about how to use formulas then to find horizontal and vertical asymptotes.